Bart Ramsundar, a computer scientist who works at the intersection of machine learning and science. Welcome to the Data Exchange podcast.
Thank you for having me on. It's kind of a pleasure to be here. I'm looking forward to kind of chatting about some interesting, topics today.
Yeah, and I don't know if you remember this, Bart, but we first met through our mutual friend Reza Sadeh when you were brought on to help him write a book on deep learning in the very early days of TensorFlow.
Hmm.
Um, but even at that point, you were already working at on scientific related projects. But actually, before we get into machine learning and science, out of curiosity, your degrees are in math and computer science, so you are definitely more on the computer science side. So, how did you end up working on science stuff?
That is a really good question. So I think honest answer to that, I was lucky enough to get kind of a full fellowship to the kind of PhD called the Hertz Fellowship. It emphasizes a lot about kind of like, solving applied problems in the real world. And one of the nice things about the fellowship is that in the cohort you get all these like really brilliant scientists from all these different fields. So like the first year of grad school, I was just exposed through my fellowship cohort to all these like brilliant biologists and geologists and chemists, and it just got me really interested because before then I'd kind of imagined that the only pathway was doing my like CS PhD degree, then joining Google or something like that. Not that Google doesn't do science these days, but it broadened kind of what I was interested in. I was having trouble finding an advisor that I really gelled with in the CS department. So I kind of looked around, buoyed by the fact I had external funding, um, talked to a bunch of people doing interesting things, and ended up working with kind of Vijay Pandey's group at Stanford. Back then, I think Vijay's group mostly studied, protein folding, protein dynamics, some things about, small molecules and drug discovery. And I just really kind of gelled with the group, kind of liked some of the things they're working on, and felt like I could make a difference. So that was probably the start of getting involved with actual science.
So let's now dive into machine learning and science. So first of all, science, you've got the scientific method, you've got experiments. So people know about the old school lab notebook and writing things down, writing results down and stuff. So at what point did the machine learning start really getting into the scientific toolbox?
That's a really good question. I'd say, depending on who you ask, people might answer decades. I know, say, in the pharmaceutical industry, people have long used statistical models to predict properties of molecules. The name for this was called a QSAR, quantitative structure activity relationships. This has been around since the 90s, I'd imagine. I think at like particle accelerators, people have used various data processing methods and statistical techniques for decades again. So I think like LHC or kind of its predecessors have long used, I think, things like random forests to filter out kind of potential, false hits from their data. So, one argument is that it's been there a long time, like definitely the 90s. I will say there's been a dramatic, uptick in the set of use cases for scientific methods. Um, boost, I think, was from like image processing. So I think you can just use image processing methods like ConvNets everywhere. You can microscopy, for example, has just been revolutionized by the fact you can begin to do automated analysis of images. Also, I think astronomy, like just like same idea except bigger scale. Last in the last few years, I think people have realized that basically any scientific instrument, it's essentially a new data processing challenge. So you have things like cryo electron microscopy has like new machine learning models. You have things like spectroscopy. You have things like genome sequencing, of course. All of these increasingly use kind of machine learning models within the physical device itself, even. So I think that increasingly as modern science has moved away from like analytical pen and paper models to kind of more automated data gathering, I think machine learning naturally has had a much dramatically expanded role. All the omics, like metabolomics, like proteomics, like large bio data gathering experiments. Basically, the more data you have, the more machine learning you need.
So here are a few early personal encounters I had with not necessarily machine learning, but data in science. The first is in the very early days of Hadoop and MPP databases. I ran into someone who worked at Slack, which is the accelerator at Stanford. And I think they were already in conversations with some people in the Hadoop world, but then as he explained it to me at that time, actually, our data is even bigger than Google and what these systems that you guys are trying to build out in the open source are trying to support, right? Number one. And then number two, the other thing that I noticed early on was, at least in the I guess you would call it text mining world, right? So with the introduction of things like topic models, many of the early examples they had were like, topic models for articles in scientific journals.
Yeah.
But that's so. Then I imagine then that probably struck the scientists. This might be useful. Maybe I can point a grad student that learned some of these techniques, right? So, but on the other hand, the examples that you mentioned, and even the physics examples, so most of the data, Bart, is it fair to say they're somewhat semi-structured data?
Yes, I think very much so. Like you mentioned kind of a very interesting thing about the there's been a long-standing dream that what if we just had a Google for papers that would just digest all the research papers in the world and answer our questions. Um, and I think text models have gotten better and better, but I would still argue that it's better to read it yourself and digest your own insights rather than an external model beyond, say, a core search engine. I do think that the biggest applications really are in these semi-structured data streams. You have some inductive bias about, okay, I know this is an instrument, it's measuring this thing, it ought to follow these laws. And that lets you, I think, construct a very tight machine learning model that doesn't have to be black box. You can kind of control for artifacts very effectively. Um, I think that in some ways, like people have been doing this for a long time. So if you look at in the pharmaceutical industry, high throughput experimentation started in the 90s with like robotic, they called it, high throughput assays. And there they used a bag of statistical techniques to like filter outliers. Right now, basically what I think people are doing are more sophisticated versions of this. Rather than a simple statistical outlier model, maybe you have a more kind of sophisticated error detection deep model that looks at an image or something and like estimates errors. But yes, I think semi-structured data, I think is more likely to have an immediate impact.
So in the case of physics, you have places like CERN and SLAC, where you have physical experiments. So they're actual real world experiments. So in the pharmaceutical and biotech fields, is the data from physical experiments, or are they simulations and kind of not real in some ways? So in which case, the machine learning model is limited by how good the simulator is, right?
No, that's an excellent point. People have done machine learning to analyze simulations. I think for the reasons you mentioned, that it is, I think, more effective to just look at real data. Like the simulator has its own biases, like its own approximations. Like if you look at something like AlphaFold, like it really does use like a whole bunch of like experimental crystallography data. Now there's an asterisk there because like although the crystallography data it looks at is the output of an experiment, it was processed by a statistical model in order to kind of smooth out errors. So you could argue that you are looking at like a simulated model output of the true crystallography experiment, but it's closer than a pure simulation, as there is like a real hard experimental measurement that underpins these systems like AlphaFold.
So, what is the state uh, of education in the science disciplines right now, as far as machine learning? Is it, uh, and I guess obviously the answer will vary by field and by subfield within the field. But are you beginning to? Is it fair to say that most graduate students, for example, in chemistry, are taking one ML class?
Hmm. I would say increasingly so, yeah. Like I think there's recognition that machine learning is like an increasingly foundational field.
And
Um,
Bart, before you continue, so
mhm.
is this new?
Yeah, I'd say so. I think it's a shift in the last 5 to 6 years. Before then, let's say you were like a experimental biologist, you probably would not bother taking these courses. It's outside your purview. But kind of last week, I had a chance to chat with a couple of like new experimental biology students. One of them was taking actually a full year-long sequence in like machine learning methods, and the other one, while she wasn't, was actually doing some legwork to try to understand on her own what was going into these systems. So I think it's increasingly of interest to you know traditional scientists, and like I think students increasingly will come in at least. Maybe they won't master it because they just haven't had the time, but they will at least I think have a working knowledge going forward.
Now, obviously, there's machine learning, but there's the actual ability to carry out machine learning experiments and in modeling and stuff like that. So I know that at least in Berkeley, there's always, the the Rice Lab and the AMP Lab before that was always conscious of, we should try to build tools that are accessible to more than computer scientists. So in
Mm.
particular, Bart, how do we make cloud computing accessible to scientists, right? So,
That
I
is
mean,
a
you and I struggle with AWS UI ourselves, right?
I was just going to complain about, SageMaker or something like that. Yeah, like these systems are quite challenging to use yet. Like I
But as you point out, science is increasingly going to have to rely on
yeah,
massive amount of compute, right? So the on-campus resources may not be enough, or and
yeah.
also it might be easier for you as a grad student if you can just spin up some resources on the cloud.
It's a so this is like a really good question. Like I think that so like I would wager that for most grad students even now, I think the cloud would be a secondary option. And I think the reason for this really is like high GPU prices. If you are say like using spot instances, you can actually get a pretty economical setup. But I think there's enough machinery in using a spot instance that it's not straightforward. If you're using kind of an on-demand instance, it just starts to get really expensive. So if you're kind of a PI of a lab, you'd look at your cloud bills and you say, let's just buy like a GPU box. So most new PIs I know actually just like take a bunch of their like startup capital. That's what they get when they start the professorship, and they invest in a lab collection of GPU boxes. Often I think like they'll just buy each new grad student like a heavy duty server. Um, so I think this has its ups and downs. It keeps costs low. It's kind of easier to explain to the university that, hey, I bought a server. Here's a physical thing in my room, in my student's room, versus here's like a giant AWS bill of like dubious accounting sometimes. Not to cast any shade on AWS billing practices. Um, so I think it's that I think cloud vendors have actually not done a great job of like reaching out to the academic community. They tend to charge, I think, the same rates. I think that, were I, someone at AWS sales, I would probably sit down and say, we should probably go out to our friends at, Berkeley, Stanford, you name it, and offer them like a steep discount. One, it's social good. We're kind of funding good causes. But two, like most grad students come out as a PhD like working on their individual servers, and they go into like a company and they're like, oh crap, what is all this like stuff? With a few exceptions. So I think this is really a failure on the part of like, the outreach and educational wings of the big cloud agencies. But maybe they have, I know AWS recently has more, AWS research grants, but my understanding is it's still hard, I think, and they haven't really penetrated the academic market.
So is AlphaFold the tip of the iceberg or a leading indicator of what's to come in terms of scientific research, Bart, in terms of
Yeah.
so the way it's been described to me is it's actually more than the ImageNet moment for computer vision. So it's magnitudes, orders of magnitudes more impressive than that particular breakthrough.
I think that, I think ImageNet is more impressive than people give it credit for, because I think vision is just such a broad modality. But I think the metaphor does hold broadly, in that I think this is like
Yeah,
arguably the first foundational
no,
advance.
in terms of I think it was the reference was in terms of the improvement was a lot more.
Mm.
Yeah.
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 Oh, yes. In that case, I think, yes, very much agreed. Like, I think this was, I back several years ago in grad school, I worked on like a deep learning for protein folding system. And we had like a few lab GPUs, and this is a well-funded Stanford lab. And we just gave up at some point because we realized like the amount of like cluster jobs we need to run, it just was not feasible. So I think with AlphaFold, it's just the engineering, the compute. It's analogous to something like GPT-3. I think it's going to be a foundational advance. It's arguably, I think, the first AI breakthrough in science. Um, I don't think it'll be the last by any means. Yeah.
So does that mean though that um, science will be kind of a compute arms race, and then it'll be a handful of groups?
I think that if you look at something like particle physics, increasingly, like, you need to be at CERN, you need to be at SLAC, you need to be at one of these big institutions. I do think you'll have a little bit of that. Like, if you're not in a place with access to compute, there's still very good research you can do, but it'll just be, say, more mathematical, more, you know, maybe you can come up with clever algorithms, but there will be a class of advances that you just won't be able to gain access to. Um, I don't know of an easy way to counteract that. Like, going to the particle physics community, there's been a long movement towards what's called the tabletop accelerator. And there's actually, I think, a very interesting line of research there where you can begin to do more experiments on a lab bench, but it's still not the same as CERN or SLAC. I think it'll be similar. I think you'll have better and better resources trickling down to kind of small academic groups, but they can't necessarily compete with their deep mind, well-funded crack team. Um, that said, I think I think that things like AlphaFold worked because CASP had this like long-running competition. There's a clear benchmark. There's a clear target. I think for foundational scientific advances, let's take CRISPR. I think CRISPR wasn't even a thing until it was discovered. You're like, oh wow, you can actually gene edit with these like repeating like things. Like it's so I think that there's a class of advances where I don't know how to do them with AI. Like I think creativity is still out of the box. But if it's something that is like here's a well-scoped problem that is just really hard, I think you can like start to hammer it with the AI hammer. But if it's something like what causes Alzheimer's, there might be ways to use the computational tools in creative ways. Like maybe AlphaFold, you could look at every protein in the brain, fold it, and then try to like understand. So there's things you can do, but I think there's this human element of creativity that I don't necessarily think a excellent scientific team at a small university couldn't do better than, DeepMind. So I still think there's plenty of ground for like small groups, but there will be some big problems that they're kind of locked out of.
Yeah. So speaking of which, so actually, as you were answering that, it dawned on me that my question was ill-posed in the following sense, because I think it only, in many ways, what I was describing were problems in science that required a lot of compute and a lot of data. But I imagine, Bart, that there's a whole lot of interesting scientific problems where the amount of data isn't that big, and so therefore the amount of compute isn't that big either, right? So
Yes.
it's a lot more accessible to many more groups, right?
That's a So there often I think it's like typically if there's not much data, it also means that the experiment is quite hard. and there's only a few groups in the world that can pull it off. So I think there's a bit of a trade-off there in that there's kind of this like you could almost view it as some type of like curve. When it's like really hard to do, there's like 5 people in the world who can do the experiment. Then it becomes easier and easier to do, then you have like most accessibility. Then it becomes so easy to do that the amount of data requires like heavy, expensive compute. And then it's actually inaccessible again. So I think there's this like Goldilocks point where it's just right. And it's accessible but not prohibitively data generative. But I think in either axis, it can actually become pretty kind of exclusive again pretty quickly.
And then going back to the topic of simulations and digital twins, I guess as you point out, if your simulator is so good, that means you spent so much time building your simulator, you probably could have had a breakthrough before you got to the point where your simulator was so good, right?
Yep. There's,
I mean, for it to simulate all the physics or all the chemistry that you need, then you probably could have gotten a breakthrough before your simulator got to that state of almost perfection, right?
So I think there's this one really interesting trend that is actually like what you can call a differentiable simulator. I think the best example of this out there is this project from Google. It's called JAX-MD. As in it's a JAX molecular dynamics. So basically it took a simulator for like simulating molecular interactions. These were very widely used to understand how proteins behave. And it basically made it into a deep model. So the entire simulator is written as like this like deep model, and you can actually learn the parameters of the simulator from real experimental data. So this is like a really nice like intermediate where you can imagine you have a few generic simulators, but then you just kind of tune them on real world data, and then you can run them at scale. Now, the challenge right now is that there's a profound computer science challenge in that my friends who do this tell me it's like 50x slower than the actual hand-tuned simulators right now. So I think there's a really hard compiler's problem right there of like, okay, how do we make something that you can actually learn, take gradients on, but also actually executes fast? And I think there's a profound challenge. I think Google and XLA are trying to take this on right now. I think that when you do that, though, I think it'll open up another next frontier because I think there's all sorts of simulators out there, but they're all hard to tune. There's this group at Stanford several years ago, Marcus Covert's group, who wrote a simulator of an entire cell. But it was like my understanding, and I might be misquoting the group, was that it was so hard to tune the thing that like they spent so much time trying to like fit these like 10 parameters and they just kind of moved on. Whereas I think if you could use this JAX-MD style Google approach, you could imagine a future in which you have like differentiable cell simulators that you can just like auto tune and then you can run really fast. So I think that's like maybe the next nascent wave several years out that could have like a giant impact. But yeah, if you're doing simulators today, either you spend a lot of time tuning it or you expect that the simulator is at best a proxy that's like a rough guesstimate.
Can't you use reinforcement learning to tune it?
Oh, that's good. I think I don't want to misquote the latest in RL, but I think it's so sample inefficient, right? Also, your work at any scale, you've probably, or other places, you've probably seen more RL deployments in the live. So I might have to punt to you on that one.
I think if you probably should incorporate some prior knowledge, otherwise you'd be wasting a lot of cycles, right?
Yeah.
Actually, speaking of which, Bart, as far as machine learning in science, right? So we talked about that in science. Actually, there's also a lot of semi-structured data, and for semi-structured data, it's not clear. It's not clear that deep learning is a winner all the time, right?
Mhm.
So does that mean that in science, when you say machine learning, it's more than deep learning?
That's an excellent question. I will say random forests are continually useful. Like whenever I hop a new area, I just hit the random forest. It finishes in 10 minutes flat, and it's probably 80% as good as anything I can come up with a ton of effort. Um, at the same time, I do think right now, like if you really want to juice performance out of a system, I think the deep models tend to win in the end. So usually for any new problem, like I think there's a cycle where the random forest is really good for a long time, then you figure out all the deep tricks and hacks, and eventually the deep net gets just considerably better. So I also think the ability to just take gradients automatically is such a superpower. So, if you code something in something like JAX, maybe it's not a deep network per se, but it's like using auto differentiation. It's kind of like coding some other algorithm. Is that a deep net? Is it not? It's kind of getting into this like Rorschach test of like how do you parse this thing? So, long answer short, I think that deep methods slash auto differentiation slash differentiable programming are like the way to go. But I anticipate no one's dropping their PCA or random forest anytime soon.
Or don't sleep on XGBoost, right?
Oh yes, another superstar right there.
Speaking of which, so your open source project DeepCam has been around, and actually many of our listeners are not familiar with it. So let's first describe what is DeepCam and who is using it and what are they using it for.
Yeah, absolutely. So DeepChem was a project I started in my PhD several years ago, about 2015 or thereabouts. The idea was to essentially rebuild at the beginning some deep learning models that were useful in some chemistry drug discovery applications. Since then, over the last several years, it's kind of had a community that's been steadily growing. At this point, I think it's like a full-fledged toolbox for really like large portions of drug discovery, materials design, some amounts of bioinformatics. Really, we're trying to.
So this is universities and private companies are using it.
Yes, so we have a pretty broad range of users, probably a little bit more academia, but a large collection of like startups and like even big companies that have used it for various things. Um, it's all MIT licensed, very broad usage. We have kind of a welcoming community. We try to.
So what are some of your headline, or what are, if you were going to give a DeepCam presentation and you have a few slides to list out some examples of how it's been used, so what would you choose as your examples?
So I think the biggest problem, single thing in DeepChem is we host a MoleculeNet benchmark suite. So MoleculeNet is roughly like ImageNet for molecules. In DeepChem, we built out infrastructure so anyone who imports DeepChem can auto-load a MoleculeNet dataset for benchmarking. This has had a pretty wide impact. I think a lot of the work in the machine learning for molecules field uses MoleculeNet to do its benchmarking work. That's probably our single biggest impact. I think the second biggest impact we had was probably popularizing GraphCons in kind of this molecular machine learning field. When we started, I think we were the only real quality implementation of graph convolutions out there in open source. Recently, that's begun to change with like PyTorch Geometric and DGL. So we're also partnering with some of the DGL developers to increasingly swap over from our handwritten kernels to like their optimized kernels. But I think that's another area where we had a good bit of impact. I anticipate moving forward material science. So there's there's definitely a few professors and folks working in that field who've started using it for things like battery electrolyte design or like other applications. So I anticipate that's going to be another growth area for the community moving forward. Pardon me, I think I have a spam on there. Yep.
So who's the user of DeepCam in a group? So in a group, let's say in a company or in a lab, is there a designated Bart who's the programmer, or how accessible is it, in other words?
So one of the nice things about DeepChem is we have a very extensive collection of tutorials. So we have something like 25 different tutorials that introduce the science behind DeepChem. It's all like written in Jupyter Notebook / Colab. So anyone can run it kind of on the web. We've also wrote a book, Deep Learning for the Life Sciences. We've tried to make it pretty accessible, and I think we've had good success in, bringing. Typically, like our users do need some amount of like, computational sophistication. Like if you're not comfortable with Python, it's hard for you to use DeepChem. Although there are a few people who are, even now using DeepChem as really their first introduction to even like the Python machine learning world. So I'd say it's pretty accessible, but I'd say we have a lot of room to like grow and make it more broadly useful. Usually though, like I think that there are typically, I think most computational groups, you tend to have the computational people clustered together under one PI. it is less common to have like, full experimental group with one computational person. That person just gets lonely and their PI doesn't know how to help them. So it's a tough situation. So I'd say less of that, but there are a few like counterexamples where we have like one really good computational person doing work with experimentalists. Um,
So what's the geographic profile of DeepCam in terms of, is it mainly US and Europe?
it's quite broad. So we have a weekly developer call, and we used to, in California tradition, put it at like 3 p.m. Fridays, back when this was a purely Stanford project. But increasingly, we've had a considerable growth in the international profile of the community. So we've actually split it up into two calls at different time zones. So we have one for like purely Asia Pacific, India, which is like Thursday evenings, California time, and
So
we have one.
which countries in Asia Pacific?
So we definitely have active developers from Japan, China, India. I know we have a couple of people in Indonesia who've like played with it. We definitely have a couple interested folks, say from like Nigeria, various countries in Europe. I'd like to say Monaco, Switzerland, UK, maybe Spain, Canada, the US. So we have a pretty broadly distributed profile. It's usually kind of like, of course, wealthier countries where there's like an existing scientific base. Um, but I think that it's pretty accessible, and I think it's like a pretty globally distributed community at this point. Eastern Europe too, I should mention. Yeah.
So do you think that have you ever come across at some point this it sounds like DeepCam is really making inroads in certain labs and certain industries, which means people are getting trained using it, which means the next logical step there, Bart, is we might start to see job postings with mentioning DeepCam.
I think it wouldn't be entirely crazy. I think there are definitely a few companies that have like been looking for this. It's kind of niche right now.
Yeah.
I think that, a big part of this has been that over the last year, we've been putting considerable effort into modernizing and stabilizing DeepChem from an academic library into something production ready. We're not 100% there, but yeah, there are definitely companies who are using DeepChem in production workflows. So I think, yes, that will come, but I think that honestly, we have more work to do on stabilizing the production. Like, so for example, like, I'm not sure if you followed this whole Travis CI shutdown. That kind of took our entire continuous integration suite offline. Or, hot patching at GitHub Actions, rapid migration right now. There's just a lot of little things like this where if you're an open source project run on a shoestring budget, you just have to scramble at these types of things. So I think it's more, we need to figure out how do we really harden this for the production scale. And I know like, some open source communities like Ray, others have really succeeded at this. We've gotten a lot better, but I think we still have a little bit of room to grow. But yeah, I think it wouldn't be crazy at all that a few years down the line that DeepChem skills are like a marketable thing you put on a resume.
So here's a question I ask every open source project leader I have on this podcast. What metrics do you care most about, Bart? Besides GitHub stars.
Excellent question. One thing that I care about, and this is like, this isn't like maybe a standard metric, is like papers published using.
Oh yeah, that's a good one.
So we try to like, we've actually just had a couple of papers, from like DeepChem active developers get accepted in the machine learning for molecules NeurIPS workshop, which is last Friday. We probably have a few more kind of coming into line. So I think that one term I've been trying to like try out is calling DeepChem a decentralized research organization, as in we have a collection of scientists, developers, students who've like many of whom have never met each other, but we all collaborate, we build things together, we write papers together. So it's yeah. So one thing I'd love to see DeepChem grow on, beyond of course the GitHub stars or whatever, is like doing real meaningful science. And I think it's very hard because you need money. So I think also looking into things like how do we get grants? Could we perhaps set it up as a formal nonprofit? There's a few avenues we're exploring. But I think
So how do you? So in order to do that, who do you need to evangelize to in the scientific community?
that is an excellent question. I think it's like first place is like PIs. Like you need to get PIs comfortable with the idea of their students spending part of their time working on DeepCam. And usually this works like through social bonds, as in like either you have a senior student ready to graduate who's already pretty autonomous and does their own thing, or you have like a very junior student who's not actively working on a PI's project.
So on the DeepCam site, you know how other open source projects have a page on their site which something like powered by, and then they list all of the companies who are using the open source project. So I wonder if you folks can have something like that, which would be papers written or projects accelerated or helped by DeepCam.
Mhm.
And do you have enough of a critical mass of such things to have a page?
I definitely think so. Like a couple of weeks ago, I randomly came across a Cell paper on my like Twitter feed that turned out they'd used DeepChem. I've never met these gentlemen or gentlemen. I think they're UCSF. And so we definitely, I think, have a critical community. Or another example, I came across like a poster and there's like a small DeepChem logo. I was like, oh, cool. I actually don't know these people. So I think we do actually have a pretty broad research footprint in terms of like work we've influenced or impacted. We have not yet gathered like the collection of papers to really like demonstrate our scientific impact. I anticipate as we apply for grants or things, we'll definitely start doing that and asking people to tell us how DeepChem has made a difference for them. But yes, I agreed. I think this is something we need to put up and have like examples of where DeepChem has helped.
Yeah, and you can even have like the in the description of the paper, uh, the description of the paper can be framed in such a way that it's accessible to a broad audience,
Mm-hmm.
right? Um, hey, by the way, in closing, do you remember that paper with Peter Norvig and a bunch of folks, the unreasonable effectiveness of data?
Yes, yeah, classic.
So, uh, what do you think about that in the context of science? The unreasonable effectiveness of scientific data.
100% holds true. If you look at AlphaFold, it only works because people figured out how to gather cryo-EM and crystallography data at scale, and you had a critical buildup, and then all of a sudden you could solve protein folding, which you couldn't before. I anticipate the same holds true for every scientific discipline. The more measurements you can take automatically, the easier it is to auto-derive some theory that explains that data. Um, yeah, I think that the same pattern has held true for years. It'll continue to hold true. I think for a lot of scientists, I think scientists are broadly just beginning to realize that this is actually a thing. I think AlphaFold will spur an entire generation of next discoveries, where you'll have people in all sorts of fields thinking, maybe we could AlphaFold this. Like we need a different type of data. We need a different type of like mathematical model. But yeah, it 100% true.
So, Bart, for machine learning engineers and data engineers who are listening to this episode who are inspired, intrigued, and say, hey, how do I shift from ad tech or recommenders to the types of problems Bart is describing? I mean, because I don't want to go back to school and take biochemistry classes and stuff. So how do people who have the computing chops enter this field? What's your advice?
Get involved with DeepChem. So we have, weekly developer calls. Everyone is welcome. It's open to anyone who's interested. Um, Stop by, say hi to people. We can definitely use your help. If you're a software engineer, we have all sorts of horrible continuous integration and testing challenges that we could use your help on. From there, like we've had a few developers get started that way, then work into scientific problems as they gain understanding of the code base. I also mentor a number of different students working in different areas. Like usually if you're willing to donate your time, I'm happy to donate my time back. We can figure out something. So yeah, try to get involved with our community. Beyond DeepCam, I think There's a couple other communities like the Materials Project, which is another open source effort to like gather material science data sets. We rely on a lot of their tooling like PyMatGen. There's a few, I think there's like AstroPy for astronomy. There's definitely a few kind of nascent open source science communities that are beginning to take shape. We'd love to have you at DeepChem. If you're interested, please check out, say, some of our like cousin projects, like these other efforts in the sciences. Usually, I think open source, if done right, can be very welcoming. And we try to create kind of an inclusive, welcoming, diverse environment. So this is something I personally care a lot about. So and I know our other developers do as well. So yeah, I'd say just say hi and get involved. So usually people are very happy to have newcomers. And there's no shortage of work. Open source, you always need more people to help is the truth.
But do you think that because someone like you've been in kind of applying ML to science for so long, but someone who knows very little science, um, is that going to be a drawback?
I think it's definitely, I think that it can be hard, I think, for someone without any scientific background to kind of enter science. I know it took me several years before I felt comfortable. I think that good mentorship, good peers, good collaborators can really make a giant difference. I think most of the science I learned because lab mates were willing to sit down over coffee and teach me things, or Wikipedia, or like, off the cuff conversations. So it is hard, which is why I do recommend kind of like getting involved with some community, be it the the formal, go to grad school type community, or the informal open source networks. Because yeah, I think I think science runs on this like old school mentorship model for a reason. Like you learn science by watching a scientist do science, uh, and it's not so easy to formalize. But yes, it is a challenge. But I think the best way is to make friends and like learn from your peers and mentors and mentor others. I think is also another way to learn.
And with that, thank you, Bart.
Thank you for having me on, Ben. This was a pleasure.